video, we will talk about joint probability distributions in statistics. There are situations where we may find it desirable to record the simultaneous outcomes of several random variables. For example, we might measure the amount of precipitate P and the volume V of gas released from a controlled chemical experiment, so give rise to a two-dimensional sample space consisting of the outcomes P and V. Or we might be interested in the hardness H and tensile strength T of cold-drawn copper, resulting in the outcomes HT. So in a study to determine the likelihood of success in college based on high school data, we might use a three-dimensional sample space and record for each individual his or her aptitude test score, high school class rank, and grade point average at the end of freshman year in college. So joint distribution for discrete random variables. So generally, if x and y are two discrete random variables, the probability distribution for their simultaneous occurrence can be represented by a function with the values f, x, y for any pair of values x and y within the range of random variables x and y. So it is customary to refer to this function as the joint probability distribution of x and y. So in the discrete case, we write fxy means probability x equals x and y equals y. So that is the values fxy gives the probability that outcomes x and y occur at the same time. For example, if an 18-wheeler is to have its tires serviced and x represents the number of miles these tires have been driven, and y represents the number of tires that need to be replaced, then we can write f, for example, f 30,000, 5 means the probability that the tires are used over 30,000 miles and the truck needs 5 new tires. So the formula, a definition for the joint probabilities is written as the function fxy is a joint probability distribution or probability mass function of the discrete random variable x and y if fxy larger than or equal to 0 for all x and y, and sigma x sigma y, so fxy summation over y and x all possible values equals 1, so which means all possibilities for this discrete pair of x and y equals 1. And for single x equals x, y equals y, their probability is fxy. So we take a look at an example of the joint probability distributions for discrete random variables. So two ballpoint pens are selected at random from a box that contains 3 blue pens, 2 red pens, and 3 green pens. If x is the number of blue pens selected and y is the number of red pens selected, so find the question A, the joint probability function fxy. B, probability xy in the area of A, where A is the region x plus y less than or equal to 1. So the solution is, first, we list the possible pairs of values x, y, and they are 0, 0, 0, 1, 1, 0, and so on to 2, 0. So now, for F01, for example, represents the probability that a red and a green pen are selected. So the total number of equally likely ways of selecting any two pens from 8 is 28. So total counts for the sample is 8 combination of 8 2 equals 8, 28. And the number of ways of selecting one red from 2 red pens and one green from 3 green pens is 6 ways. So F01 equals 6 of 28 equals 3 of 14. So similar calculations can be applied for the other cases. So the formula to calculate fxy can be written as combination of 3x and 2y, then 3, 2 minus x, 2 minus y. Then denominator is 82, right? Because this is the possible way, the biggest possible way of selecting two items from 8, right? And numerator is the selection for each group. Each group means different color: blue, yellow, blue, red, green, right? So this table will list the different probability distribution for the different x and y. This contingency table, and the total probability will be 1. And this is the marginal also. So the question B is for the area x plus y between 0 and 2. So the joint probability for x and y can be written as, for this region, x plus y less than 1, so equals f00 plus f01 and plus f10, so equals 9 of 14. So next we look at the joint probability distribution for continuous random variables. So when x and y are continuous random variables, the joint density function fxy is a surface lying above the xy plane, and probability xy in area A is any region in the xy plane is equal to the volume of the right cylinder bounded by the base A and the surface. So because in the continuous probability random variable, each density is 0 for any random variable x and y, or the combination of x and y, right? So we only can calculate the probability of the random variable between a region. So the function f(x) and y is a joint density function of the continuous random variable x and y if fxy larger than or equal to 0 for all x and y, and integration of xy over dx dy for all possible values from negative infinity to the positive infinity equals 1. Because density curves on the density curves area will be 1. Then for any region A, Pxy in the region A is fxy, this density function, joint density function, take integration over dx and dy in this region. So the example is a privately owned business operates both a drive-in facility and a walk-in facility. On a randomly selected day, let x and y respectively be the proportions of the time that the drive-in and the walk-in facilities are in use. And suppose that the joint density function of these random variables is fxy equals this part in this region and 0 for any other region. So verify condition 2 of definition of joint density function. And question B is find probability of x and y in the region A, where A is x between 0 and 1 of 2, and y between 1 of 4 and 1 of 2. So the solution for A is we take integration of fxy over dx and dy. So with the mathematical manipulation, we can verify that it equals 1. So this complies with the definition of joint probability distribution. And for the question B, we just calculate the probability in the region A, also take integration. With several steps, we can get a result is 13 of 160. So the marginal distributions. So given the joint probability distribution fxy of the discrete random variable x and y, so the probability distribution gx of x alone can be obtained by summing fxy over the values of y. So we can sum y out to get the probability distribution of gx. Gx is also called the marginal distribution of fxy. And similarly, the probability distribution hy of y alone can also be obtained by summing fxy over the values of x. So we define gx and gy to be the marginal distributions of x and y respectively. So when x, y are continuous random variables, summations will be replaced by integrals. So for the marginal distribution of discrete random variables, gx equals sigma fx and y over y, and hy equals sigma fx and y over x for the discrete case, and for the continuous case, gx equals fxy take integral over dy, and hy equals fx and y take integral over dx. So the example shows that the column and the row totals in example of blue pen, red pen, green pen, and give the marginal distribution of x alone and of y alone. The solution is, for the random variable x, we can say g0, which means for x marginal, then equals all y values take summation with same x, right? So f0, 0, 0, 1, 0, 2 equals about 5 of 14. And for the g1, we can also use similar way, g2 also. So the result for the marginal distribution for x is look like this one. And we can also calculate the marginal distribution for the y. And for the continuous case, for example of driving facility and working facility, you can get the marginal distribution of gx using integral of fxy over dy. And the result is 4x plus 3 divided by 5 for the region x between 0 and 1, and equals 0 for other x region. And similarly, we get the y marginal probability distribution using fxy integral over dx, and the result is 2 times 1 plus 3y divided by 5, and available region for the y is between 0 and 1. And the marginal Density for the y is 0 for other y region. Thanks for watching.